Carly's not back yet. We need to wait on her.
Okay, so we are going to talk about derivatives of exponential and logarithmic functions. So some universities do exponential and logarithmic functions in Calc 1. Some do it in Calc 2. Eastern Gateway requires that we do it in Calc 1, so we're going to do it. The formulas are pretty nice. They're not super complicated or anything. Just like our trig functions, how we have like the derivative of a sine as a cosine, and we have those rules. Exponential and logarithmic functions just have their own rules that we have to follow. Okay. So the first one that we have to follow is that a derivative of an e to the x is e to the x. Yay. It almost in a way acts like a constant with like an x tacked onto it. So the derivative of e to the x is e to the x. But if there is a function stuck up in the power, that is the stuff that is stuck. So you do what we normally do. The derivative of an e to the x is e to the x. So the derivative of a function is e to that function times the derivative of the stuff. Okay. So if we have a function like 2 times e to the x, the derivative of that is 2 e to the x. Awesome, great, wonderful. Okay. If we have a derivative with a function in its exponent, so the exponent is a function of x, like g to the x, the derivative of that uses a chain rule. Now, how does a chain rule work? Well, we know that it is just that function's original rule with the stuff stays there. So the stuff is going to stay there. But then we have to multiply by the derivative of the stuff. So it would be 2 plus 2x. Okay, so e's are wonderful. They're one of the easiest type of derivatives to do. The derivative of e to the x is e to the x. The derivative of e to the function of x is e to the function of x times the derivative of the function. So it's a pretty good rule. For me. No, they're just mine. Just cause. No, actually, I bought some of them for a few of my friends, but look at these ones. I'm distracted. Each one has a little different face.
That's so cute.
Isn't it cute? Aren't they cute? This one's a happy one. I gave one of the happy ones away already.
Oh, they're all happy except for the one.
Yeah. He's like, oh. Anyway. Well, we won't include that in our... No.
No, just like right here for now.
Okay, which one?
The right one.
This one?
Yeah, that one.
Okay, he can...
Oh, thank you so much.
He can stay there and stare at you. Okay. So let's just practice a few. If you see the derivative of e to the tangent of 2x, that's a chain rule. The derivative is going to stay e to whatever that original function was, because that's the chain rule, but you have to multiply by the derivative of the stuff. So the stuff stuck inside is the tangent of 2x. The derivative of a tangent of 2x is another chain rule. The derivative of a tangent is secant squared of 2x, but then I have to multiply by the derivative of 2x, which is 2. Okay, so that is how you do example 374. Pretty straightforward stuff, nothing too fancy. 375. 375 requires a chain rule. 375 requires a chain quotient. So it's a quotient. So remember, the quotient rule is the derivative will be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. Okay. So when we do this derivative, we're going to do the bottom times the derivative of the top. Now the top has an e in it, so the e just stays exactly like it started, but we're going to multiply by the derivative of the function that was stuck. So the derivative of x squared is 2x minus the top times the derivative of the bottom all over the bottom squared. Now, most of the time, we do not require any sort of simplification, but we're getting to the point, we're almost done with chapter 3. Chapter 4 are applications of derivatives where we need to manipulate the algebra. So let's just take a moment and make this algebra look a little nicer, okay? So first I'm going to rewrite this as 2x squared e to the x squared minus e to the x squared over x squared. So that's my first little rewrite. What do you notice is in both terms in the top? What do they both contain? E to the x squared. So that means that is a factor that can be removed. So it's not a bad idea to get in the habit of trying to start simplifying these things more than we have done in the past. And we get 2x squared minus 1 over x squared. Now, algebraically, you cannot cancel this x squared out of just this term. Kittens cry somewhere when you do that. Please don't do that. This x squared is under everything, so it is divided into everything. So just leave it. Okay. So that is example 375. Anybody have questions about that one? Okay. Now, here is a exponential function where we're going to apply some of the rules we have learned so far about derivatives. So this is about the population. And so the rate of change of the population, the derivative gives us a rate of change of whatever that particular function is portraying. So this would be the rate of change. So it says that to find that a prime of t, that the ratio of the rate of change to the population a sub t is a constant. So all that means is let's take the derivative first and let's see what happens. Let's see how it relates back to the original function. So that's what they're wanting us to do. Well, the derivative, the 1,000, is just a constant. So remember, it just kind of hangs out and multiplies by our answer. It's an e to a power of t. So the e to the power of t stays. But then don't forget to multiply by the derivative of the function that is in our power, so 0.3. So you'll notice that that is just 0.3 times 1,000 e to the 0.3t. Gosh, I'm sorry, that looks so good. Which indeed is our a sub t function. So all they're saying is that the derivative is just a sub t times some constant. It is just a ratio of the original function. So that's all they were talking about there, okay? So e derivatives are pretty good. Now, if we change the base and it's not an e anymore, there's a little bit of a twist to that. And then logarithms have a little bit of a twist to them, but we will do those things here in a second. Everybody good with that one? Okay. So the thing you have to remember about a natural log, the derivative of a natural log is 1 over x. But if it's 1 over a function, or I'm sorry, a natural log of a function, it would be 1 over that function times the derivative of that function. It works like a chain rule like we've seen before. Sine becomes a cosine. Natural log becomes a 1 over something. So 1 over the function times the derivative of the function kind of makes sense. So let me show you an example. If you want to take the derivative of 7 times the natural log of x, that would just be 7 over x. Natural log is always 1 over x. If there happened to be a constant there, it would multiply by 1 over x. So that's why the 7 just kind of hangs out. Now, if there is a function stuck inside, so if we have a function of x stuck inside, we're going to do the chain rule. So what does a natural log do? It takes 1 over whatever is stuck inside. So that's going to be 7 over whatever is stuck inside times the derivative of what was stuck. So it would really be 14 over 2x plus 1. So natural logs and e's are nice. You just have to learn the extra rule. You just have to learn the extra rules. So the derivative of the natural log is 1 over x. The derivative of the natural log of a function is 1 over that function times the derivative of that function. Just follows chain rule. So if we have here a natural log, we notice a function stuck inside. The derivative is just going to be 1 over the function that was stuck, 1 over the stuff, times the derivative of the stuff. Well, the derivative of x cubed plus 3x minus 4 is 3x squared plus 3. Now, you can put that directly on the top if you want. You could make that 3x squared plus 3 over x cubed plus 3x minus 4. Eventually, we will practice doing some manipulations if we have to. Sometimes if the top and bottom is factorable, we might factor it. For our purposes at the moment, we don't necessarily have to do a heck of a lot of changes to our function. Okay. Now, unfortunately, not all bases are e. Not all logarithms are natural logarithms. We could have a log base 2, log base 10, log base something else. So we do have to learn some other rules. But let's practice this one more time before we jump into other types. So the derivative is going to be 1 over the inside. Now let's talk about algebraically what that means. 1 over anything is just the reciprocal of that thing. 1 over anything is just the reciprocal of that thing. So if you just immediately went to that being the reciprocal, that's perfectly okay. Okay? 1 over something, the natural log takes the reciprocal of whatever was inside. So it's always going to do that. But don't forget, we have something stuck inside. What rule do we have to use for the thing stuck inside? It's a quotient. We got to use that quotient rule. Let's put a little dot there. Okay? So when we do that derivative, it's going to be the bottom times the derivative of the top. Now the top is gross because it's a product rule. So it's going to be first times the derivative of the second plus the second times the derivative of the first. So that's top or bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Okay. Now, when we multiply this times that thing, okay, let me write it just maybe slightly nicer. There's not much I can do to make it any nicer, but so that's going to be 2x plus 1, x squared cosine of x plus 2x sine of x minus 2x squared sine of x over 2x plus 1 squared. Now, When we get to the point where we need to reduce this stuff, you would want to FOIL this, you know, distribute 2x, distribute 1, get a list of things. There's probably going to be something that cancels out. For our purposes right now, I just don't care. But algebra we should know how to do by now. Now, one thing you can do immediately right off the bat, you have a 2x plus 1 here, you have a 2x plus 1 squared here. You can reduce that down a little bit, and it would just be a 2x plus 1 in our denominator. Other than that, for now, let's just leave it. Gross, right? And the reason it's that gross is just because that function they put inside of that natural log was just ugh, okay? And so it required us to have a quotient rule that contained trig functions, that contained a product, just lots of stuff, okay? So you won't run into ones that are that evil very often. So yeah. Okay, so now that we have that, I've mentioned that there's rules if we change the base, whether we don't have an e anymore or whether we have a different type of logarithm. So we need to learn those rules. So if you have a log that has a different base, so in this case log base b, the only thing different, we still do 1 over x, or 1 over the function times the derivative of the function. This is all the extra that you tack on. You just tack on a natural log of b. That's the only difference. Think of our e to the x function. Our e to the x function, the derivative of e to the x is e to the x. The derivative of b to the x is b to the x. But what do you tack on? Natural log of b. Natural log of b. So the only thing different is if you change the base, you convert it, you fix it by multiplying by the natural log of b in the denominator of a log, but just by natural log of b, plain old natural log of b, if it's a b to the x. So that's the difference. That's the fix. And it's basically because of the change of base formula that happens. That change of base formula back from pre-calc. So you have some more formulas to deal with. So let's practice some that have a different base. So in this one, instead of e to the x, it's 3 to the x. So we got to fix the problem. But it's easy. Okay. So to take the derivative, it used the rules that we already know. It's going to be a quotient rule. So put our denominator in parentheses. So our derivative is going to be the bottom in parentheses times the derivative of the top. Now the derivative of an e to the x is e to the x. A derivative of a 3 to the x is 3 to the x times the natural log of 3. That's the only thing that changes. We just get that a little extra little piece, an extra little constant. Minus the top times the derivative of the bottom. A derivative of a 3 to the x is 3 to the x times the natural log of 3. The derivative of 2 is 0. If you want to put plus 0, that doesn't hurt anything. All over the bottom square. Now, for now, I'm okay with us leaving it there. There will come a time that we will have to do some manipulation. If you were to manipulate it, I would distribute here. I would distribute here. I would make a list of terms and see if there's anything that they have that I can factor, see if there's anything that can cancel, things like that. Okay. Let's talk about the slope of the tangent line. Whether our derivative contains trig functions, polynomials, or e's or logs, the derivative of the function will give us the slope of the tangent. So it just makes sense. So we're going to take the derivative, and it's a log base 2. Now, natural logs are 1 over the function times the derivative of the function. Log base 2, we do the same thing. It's 1 over the function times the derivative of the function. But because it's a base 2, we have to tack on a natural log of 2. Now, I wouldn't simplify it a whole lot at this point, but you could write it like this: 3 over the natural log of 2 times 3x plus 1. And they want to, we'll call this f of x. They want the slope at 1, so they want the first derivative at 1. So that's going to be 3 over the natural log of 2 times 3 times 1 plus 1. Well, 3 times 1 is 3 plus 1 is 4. So it's really just 3 over the natural log of 2 times 4. Now, I would leave it that exact value unless you had to draw it, unless you had to use it any other way, maybe to find the equation of the tangent line or something of that sort. So the decimal value is not helpful unless you had to depict it somehow or use it in a real life application, okay, which we aren't doing right at the moment. Everybody good with how that one worked out? Okay. So then you're ready to try these. You're just doing the derivatives. You do not have to do any simplification. You may have to do that for the ones down at the bottom. Okay. And then we'll make some flashcards to go with these so that we have those in our bank of flashcards.